In this installment, we're going to look at the centripetal force being friction. Remember, the centripetal force can be a force, any force, that is center pointing. So we'll look at an application when that's a force of friction. I'm going to situate us where we are in the course. Of course, we have mechanics, kinematics, dynamics, momentum, energy, forces, and all our variety of forces here in the fan. Plus we have the inclined plane, and we have circular type motion, which we are looking at different cases now. So to help us understand this particular case of a car going around a turn, for example, Newton's first law states that a body will keep its current velocity unless there is a force outside the system acting upon it. So this car traveling down the road in this direction wants to keep moving in a straight line. And it doesn't. It doesn't go in a straight line. It follows this curve as if there were a circle here. So a part of this circle, in this case about a quarter of a circle. That means if it's traveling at a constant speed and goes around that turn, it is accelerating, centripetal accelerating. So if there's a centripetal acceleration, center pointing acceleration, there must be some force causing that. And in the case of cars on a road, or bicycles on a road, it is friction. So in any centripetal case, we ask, what is the force? Gravity, tension, friction, electric, magnetic. In this case, it's friction. What is that force causing it? If we look at this image I've got here, this is the blow up of a tire. And we look at the atoms in the tire and the molecules in the road like so. The key thing about the friction here is that there is no sliding. And that's what we associate with static friction, stationary friction. The molecules on either side in each material are fixed relative to each other. You might imagine now that if we made this slippery and removed the friction, the car would move in a straight line. So that leads to another way to help us identify the centripetal force. The centripetal force is the force which, when removed, the body will no longer travel in a curved path. It's the force that causes the curved path. So what is it we would have to remove for a car not to travel in a curved path when the wheels are turned? It would be the friction. And it's static friction. So let's look at some implications of this. We'll start out with our Newton's second law, with the net force is the sum of the forces. And we have centripetal acceleration when it goes around the road, so F net is MAC. And the force that's causing that is the force of static friction. Now MAC is mv squared over r. And the force of static friction is mu s times the force normal. Since we are on a horizontal ground, the force normal is equal to the weight. We have our car, force of gravity like this, force normal like this, and we have a centripetal force acting this way as it's going around the turn. Force normal and force gravity are equal and opposite to each other. So we have mu s times mg. So when we look at this equation now, we have to ask ourselves, since there is an m on both sides, are they the same m or are they different m's? On this side, it is the mass undergoing the centripetal acceleration. In this case, it is the mass of the car. Over here, when we have the mass, it is the weight of the car, the mass of the car. So these m's are indeed the same m. This leaves us v squared over r is mu g, and v squared then is mu gr. Notice that the velocity then that allows this to happen does not depend in any way on the mass. Making the car more massive will increase the centripetal force. If I double the mass of this, it will double the centripetal force required to produce that centripetal acceleration, but it will also double the mass, the normal force, and thus the frictional force. So whatever I do to one, I do to the other. There's a direct relationship. So in this case, mass itself is not a factor. That's a big takeaway in this case. Mass does not affect the velocity. But you can also see then, looking at each of these variables, by increasing the radius, we can increase the velocity. So a wider turn, we can go faster around. The tighter the turn, the slower we have to go. That's what that means. And the other is the friction. If we reduce the friction, we have to reduce our velocity. And that's why we have to slow down. And it's important then that we slow down before we enter a turn. That's exactly why. We have to slow down before we enter the turn, because then the friction is not only giving us the traction to drive, it has to give us the traction to also turn. So velocity is important when we're driving and going around turns. The mass, though, has no effect on the velocity at which we can go around a turn. If we increase the radius, that will allow us to go faster. And the opposite is also true. But by reducing the friction, we have to also reduce our speed. And things that reduce the friction are ice, of course, and snow, and anything liquid. We've already talked about that with the liquids and tire treads and the effect that those have on hydroplaning and so forth. But we have to also reduce our speed. And that is force of friction as a centripetal force.